Modern networks link billions of devices built by competing vendors across physical mediums that constantly degrade and drop signals. The challenge is the gap between what machines do physically and logically. Servers modulate erratic analog voltages, but applications require perfectly structured data payloads. Translating these fluctuations require immense computational complexity, including error correction, flow control, and formatting for every individual packet. A naive approach would be to write a monolithic program to handle the entire chain, hard-coding instructions from the voltage modulation at the bottom all the way to the HTTP rendering at the top. However, because hardware varies infinitely, this single program would have to account for every possible physical edge case. A change in the cable type or the radio frequency would require a complete rewrite of the entire software stack. The OSI and TCP/IP models provide the architectural patterns of modularity required to prevent this total system collapse. By isolating specific tasks into discrete layers, engineers can manage the complexity of global communication without the entire system becoming unmaintainable. To see why layering is required, consider a monolithic stack resting on a copper wire. Here, software logic is fused directly to hardware properties. Swap that copper for a fiber optic line, change the transmission method. The system crashes. Because the application logic at the top is hard-coded to the voltage handling at the bottom, a hardware upgrade forces a complete breakdown of the software. Modularity solves this by breaking the network problem into isolated parts that interact only through defined boundaries. In a layered architecture, the physical layer is its own module. We replace hardware-specific code without disturbing layers above. This is abstraction. Upper layers don't care if the medium is Wi-Fi or fiber. They just hand data down, expecting it to reach the destination. Abstraction functions as a bulkhead, containing the volatility of hardware changes strictly within the lowest boundary of the system. This separation of concerns also addresses the human factor of engineering. This blueprint illustrates how layering enables parallel development. Hardware teams can refine physical circuitry, while software teams write routing algorithms, both working asynchronously. These teams only communicate across the layer boundary by a strict, standardized protocols. These protocols act as the fixed interfaces that keep different modules compatible. This standardization simplifies change management. An organization can upgrade its routing software to a more efficient algorithm without having to replace a single physical switch or cable. This is also the mechanism behind device interoperability. A Cisco router and an Apple laptop can exchange data because both adhere to the same protocol interfaces at every layer, regardless of their internal hardware. Vendor-specific engineering quirks remain trapped behind these standardized boundaries, preventing a single manufacturer from dictating the entire network's design. Establishing these interfaces is the only way to maintain a unified, vendor-agnostic internet that can scale globally. Even with these layers in place, a single layer can sometimes face internal friction if its job is too broad. The data link layer, for instance, must handle two very different tasks: the software-heavy logic of data flow and the hardware-heavy logic of physical transmission. Trying to manage both with a single set of rules creates a bottleneck. The layer would have to be rewritten every time a new type of radio or cable was introduced, even if the flow control logic remained the same. The solution is to refine the layer into sublayers: the media access control, or MAC, and the logical link control, or LLC. The MAC sublayer is specialized for the physical medium. It handles specific timing and hardware signals, managing messy physics, waiting for clear radio channels so devices don't transmit simultaneously. The LLC sublayer sits above the MAC, acting as the generic software interface. It handles error checking and flow control, completely unaware of the physical hardware used below. Because the MAC has already translated the physical signals, the LLC can provide a uniform stream of data to the higher layers of the network. This separation allows the same software-level flow control to work on any hardware. We only need to change the MAC sublayer to support a new technology, while the LLC remains untouched. Sublayers act as micro shock absorbers, refining the functionality so that major layers aren't burdened by the specific constraints of the hardware environment. Despite these architectural safeguards, physical hardware eventually degrades and connections fail. In a monolithic system, identifying why a packet was dropped is nearly impossible. Since the code is one giant block, An error in the physical voltage could look like a bug in the application software. Layering fundamentally changes the troubleshooting process. Because each layer has a fixed responsibility, diagnostic tools can isolate the search space to a specific module, like Layer 2. This allows engineers to systematically rule out physical or application logic, focusing only where the failure occurred. Quarantining faults within layers drastically reduces diagnostic time, ensuring that a hardware failure doesn't cause a logic error that takes down the entire system. These same strategies of modularity and abstraction scale upward, providing the logical foundation for modern cloud architecture. Just as networking layers abstract the data path, the cloud treats the entire server hardware as a physical layer. By inserting a virtualization layer on top of the hardware, we can run any software environment without it being tied to a specific physical machine. Breaking systems into layers is the essential architectural strategy that allows global infrastructure to function as a single interoperable machine.